Nothing beats. This video, we're going to focus on continuity, but now over intervals of real numbers. Let's get going. All right, first of all, we want to talk about continuity at endpoints in order to talk about continuity over intervals. So as we can see here, in part I, if you will, continuity from the right. We say that a function, f of x, is continuous from the right at real number x is equal to a if we have that the limit as x goes to a from the right down here of the function is equal to the value of the function. So you can see the similarities with the definition of continuity from the previous video, except now we're only approaching a from the right. So graphically, what we're saying here is if we got some number a right here, some real number, then the function is continuous from the right at x is equal to a if, as we approach a from the right, the function approaches its output value here, f of a. So in that case, the function is continuous from the right at x is equal to a. You may be guessing what comes next, and you probably guessed right. Continuity from the left now. So in this situation, we say that a function f of x is continuous now from the left at the real number, let's say x is equal to b, if we have that the limit as x approaches b from the left now, right up there, of the function f of x is equal to f of b. Very similar to the previous situation. So all we're seeing here in the graph, if I approach x is b from the left now, what's the function doing? It is approaching its output value, f of b. And in that case, the function would be continuous from the left at the real number x is equal to b. So that allows us to talk about continuity over intervals now. We say that a function f of x is continuous now on some interval, let's call the interval I, if it is continuous at all the points on the interior of the interval and is also continuous at the endpoints of the interval. So basically it's just continuous everywhere on the interval. So there's 4 different diagrams we want to take a look at here, which depicts the different ways we can be continuous over intervals. So let's take a look at those. First one is the function being continuous on the closed interval, say from a to b. So that means everywhere in between a and b, we're continuous, as we can see here in the graph. However, now we see that at the endpoints at a and b, we have the one directional continuity that we were just explaining a moment ago. So in order to be continuous at the endpoints, right, we have to have continuity from the one direction. Notice at a, limit as x goes to a from the right of the function is equal to the value of the function at a. And also the limit as x approaches b from the left of this function f of x is equal to the value of the function at b. And for that reason, we have continuity over the closed interval here because the function is continuous everywhere between a and b, and then also at the endpoints in the according directions. Other things can happen though. So compare that with this next situation in which we're talking about similar, the last one, f of x here, but now we're continuous over the open interval, a to b. And as we can see here at the endpoints a and b, the function is not defined. So the limit of the function does not equal to the value of the function at the endpoints because the function is not defined there at the endpoints. And hence that is an example of a function being continuous over the open interval because it is continuous everywhere inside the interval, just not at the endpoints. How about this situation? In this case, the function f of x is continuous on the interval a to b, where we are closed at A and open at B. And we can see in the graph that indeed at x is equal to A, we have that the limit as x approaches A from the right of the function is equal to the value of the function, hence that closed dot that we see in the graph. But at B, the function is not defined, so its limit as x approaches B from the left cannot be equal to its output value since it is not defined there. Hence, we have continuity on this half-closed or half-open interval, if you will. And then finally, we see a picture like so, kind of the opposite of what we just looked at. This function is continuous on the interval a to b, but now open at A and closed at B. For a similar reason as the previous example, you notice right here at x is b, the limit as x approaches b from the left of the function is equal to the value of the function at b, and hence we have continuity at b at that endpoint, but we don't have continuity at a, again, since the function is undefined, and so its limit from the right towards a cannot equal the value of the function at a. So there's a variety of different ways we can talk about continuity over intervals. Now, to help get this idea down even further, let's take a look at this example right here. We are given the graph of a function y is f of x, as we can see on the screen, and what we want to do is list all the intervals for which the function f of x is continuous, using all the things we just talked about. So we're going to list the intervals of continuity. Intervals of continuity right down here. All right, what are they? We're just going to list them. So we can see that the function is not defined for values of x that are negative, right? It starts at x is 0, and its output value there is equal to 2. And so just like we were seeing in the previous diagrams, this function has a limit, notice, limit as x approaches 0 from the right of the function is equal to 2 here, and of course that is the value of the function at 0. So we have continuity from the right at 2. And then as we move through our graph, continuous, 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 but then we get to x is 2 and we are no longer continuous, right? At least from the left, because the function at 2 is not defined. So the first interval of continuity would be the interval closed at 0 and then all the way to 2, but open at 2. So that's that first little piece of the graph. Now we'll focus on this piece right here, just moving from left to right. Notice, again, at x is 2, when we make this jump right there, the function is not defined at that location when we start the next interval. And so we can't say that the function is continuous from the right at 2 because the function is not defined there. But as we move along our graph, la-di-da-di-do, all the way to x is 4, we have that, right there, the limit as x goes to 4 now from the left of the function f of x, well, it's equal to 2, and of course that is the value of the function at 4. And so we do have continuity from the left at 4, and so the next interval from 2 to 4 would be the open at 2, and then all the way to 4, and close at 4, indicating continuity from the left at 4. We got two more little pieces here to look at. Say from 4 to 5, well, that's this little piece as we move along. We don't have continuity from the right at 4 because the function is not going to be equal to its output value at 4 from the right. And then as we go to 5 from the left, the function is not going to be continuous at 5 from the left because, again, right here, the value of the function is undefined at that little hole. Even though it is defined to be 3, the limit as x goes to 5 from the left is not actually equal to the value of the function there. And hence, the next interval would be the open interval from 4 to 5, continuous everywhere in between 4 and 5, but not at either of the endpoints. Finally, this function continues on from 5 onwards, like that piece right there, that linear looking graph. So again, if we approach 5 from the right here, like so, the function's limit does not equal its output value. So we are not continuous from the right at 5. Hence, we're going to start our interval here at 5 as an open interval. But then as we continue on in the x direction, of course, this arrow here indicates that it just continues to behave this way forever. I can just keep going as large as I want in the positive x direction, and this function is going to just keep behaving like this line, right? And of course, that's also saying that it will be continuous forever on after that, because the value of the function is always going to be equal to the limit of the function for all values of x bigger than 5. And hence, our last interval of continuity would be the open interval from 5 to infinity. So there's a little quick video on continuity over intervals, including the idea of continuity at endpoints, and we just looked at an example to help us understand graphically how that works out. So until the next video, which will be another one on continuity, Math and Beats, I'm out.